think we've got audio working. Not 100% sure. Some of you guys out there in the chat, tell us. Got Judy Bassett in here. Hello, Dart. And right off the bat, I get one of these silly arrows saying that YouTube's not receiving enough video to maintain smooth streaming. I don't know why that keeps happening to me. Oh well. Can't have everything, I guess. Glenn Collins, good day. Well, I've managed to get a lot of data collected here in the last 3 or 4 days. Finally. Now that everything is operating the way I want it to operate. So I've got about, I've got eight full tests completed with what seems to be some rather remarkable accuracy. But I'm going to show that to everybody here in a few minutes. Right now, the machine is just sitting static there. And it's really stable. It's been like that now for, a good 4 or 5 hours, I think. I forgot when the last time was that I moved the big balls around. But in a couple of minutes, I'm going to move them again. And we'll see if we can get one more run in today or tonight. See how that works out. They'll make hello, buddy. What's going on? Just Dave. No, I haven't posted any data yet. But actually, I'm going to show you some data here in a few minutes. And it operates, just like an experiment does, anytime. Some numbers are higher than you think they should be, and some are lower. But when you do enough of them, you get an average that is pretty dependable. I'll just tell you that right now, if I had to quit right now, the testing that I've done so far, this thing has given us values for the gravitational constant within about 0.3% of the accurate accepted value. And I'll take that any day of the week. That's highly surprising. And of course, as time goes on, maybe that'll become, 1% off. I don't know. Who knows? Still hearing me, Judy?
I hear you.
Oh, okay. Any of you guys wanting to join in, please do. If you're on the Discord server, just jump on the live stream with us. In fact, I could go over there maybe and find a link to it that would work if anybody needs one. Let's see, this one right here ought to work. let me do one thing here. Make this a permanent link. Here we go. This will be good. I have to figure out how to get back to where I was. Here we go. Let's put this in the chat. There you go. Anybody that needs a link, feel free to join. Got 9 viewers right now. That's terrific. Totally unannounced. I wasn't sure I was going to be able to do this tonight, or I would have put out some notification. But it turns out that I've got a little time on my hands, and I thought I might as well let you guys enjoy some of the fun too. If anybody can call this fun. So we'll give it a few more minutes, see if anybody else wants to show up. Tell us what you've been doing, Judy.
Well, I start work today, so I'm coming out of retirement.
How are you?
Yes.
Going back in the boiler business?
Temporarily. Technical writing.
Oh, technical writing. That's a good job. Hello, Don Anders. Yeah, I'd like to have a job doing that. I think.
Maintenance manual for power plants.
Yeah. I'll tell you, I think the days of the old stuff I grew up doing, coal-fired power generating units, is coming to a rapid close. At least in this country it is. They keep shutting down power plants like crazy. Just Dave says says he gave up on proving anything to the flat earth community. Got a house to build. There you go. There's something useful. Talking to flat earthers is not useful. Let's see, just Dave, you're the wrong color. We gotta fix you. There you go. Hold on a second. I'll be right back. we go. All right, got 17 watching. Hey, Professor Phil, how you doing? Tell you what, let's get this show on the road. Let me go move the big balls around to the other position, and let's see what happens. There we go. I'm betting the little red dot is going to start moving to the left. Brian Mabbitt. So it says I'm not watching. Okay. Whatever, Brian. Glad to have you here anyway. Always good to talk to Brian. Even though he's got some strange ideas about the shape of the earth, you know. That's okay. Hello, Terry Davies. Any of you guys that want to jump on the Discord, hop in the chat with us. Let's see, I'm going to try something. Take note of where the little red dot is right now. It's looking like it's about 235 or so. And when we come back, it will have moved left quite a bit more than that. But I just want to try something real fast. Let's see if I can do it. Now I got to wait for...
You can hear me okay, Blue?
Yeah, I can, Terry.
Oh, okay.
GPS, what's going on, bud? Hopefully that's going to come up on screen here in a second. I don't know how much time delay there is in this OBS. Some, certainly.
Just seeing some calculations on the screen now.
Are you? Good, I don't see it on my live stream yet. Well.
Yeah, that's what the live stream at the
moment. Yeah, mine gets a little bit behind. That may be a little difficult to see, I don't know. Hopefully you can see it.
So, yeah, you can see it, you can read it all pretty softly.
Okay. Well, and I'm really happy with this. If you look at the little table looking thing over on the right hand side, I've got a column there with 8 black numbers in it, and the bottom one is red. Each one of those is a test measuring the deflection of the laser, and computing a value for the gravitational constant from it. And the bottom red number is the average of those 8 tests. Right now, that averages, and now I've still got to go back and do some checking, make sure I've got the data all accurately recorded. But right now, that average is 6.655 times 10 to the minus 11th, which is only about 0.3% different than the official accepted value. So that's pretty remarkable, I think, and I'm really happy with it. What's the beeping? Yeah, that's OBS doing that. I need to go in there and shut off all those notifications. That's what makes that silly sound. I'll do that in a minute if it's annoying you guys. But that's the data I've got at the moment. I'm going to go back to the camera view for a minute. In fact, let me see if I can fix the beeping issue. Basically, just turn all the stuff off, and that should make that stop doing that. Discord can do some very annoying things.
Yeah, I don't have any notifications, sound notifications for Discord.
Yeah.
I've got them all turned off.
Yeah, that's what I just did, so hopefully that'll put an end to it.
Yeah, people were complaining about my Discord because I had so many channels shielded in the Shield You Shit. They said I was going off all the time, so they turned it off.
Yeah. Yeah, it is pretty damn amazing, Professor Phil. I'm shocked. Again, I've got to go back through and make sure that I've got everything accurately recorded. I want to check these oscillation periods again. Make sure.
They were arguing over on, before I forget, they were arguing down on that Brandon Toys channel there just a while ago. I was down there with Rumpus and everyone. And they're going through through this experiment, mentioning yours in particular.
Oh,
and
yeah.
They're saying, oh, well, it's not an experiment because it's got to be controlled with, like electrical fields, and it's got to be in a vacuum, and all these other things I was trying to come up with.
Yeah, at the moment, I can assure you those guys are terrified of what's going on. I've gone through that several times today with various characters over on Jose's show and on Jim Panda's server.
You're being a bit conservative there with the title of characters, weren't you?
Yeah, just a bit. No reason for name calling though.
Nah.
So, I'm trying to be nice. This really has upset them a lot more than I thought it would. Not that I really care one way or the other. As I've said from the beginning, this is not being done for them. I'm doing it.
No.
I'm doing it for us. When somebody says, hey, how the hell could a guy 223 years ago with nothing more than just some basic hand tools have ever put together something as sensitive and accurate as that is? Well, here's how it was done. By damn, he could do it. He did do it.
Yeah, but the other component is math. The other component to the experiment is math.
Yeah, I need a
You
little
didn't have
math.
math to go with it.
Yep. My math is easy. Cavendish's math was, Jesus. That poor bastard. And I'm pretty sure he didn't have a pocket calculator. In fact, years and years after he published his paper, some guy went through it and actually found an arithmetic error that changed the results slightly. I can't remember that whole story, but...
Well, I hope it wasn't to the detriment of the experiment in its entirety, though.
Oh no, it was a minor math error. It didn't have a huge effect, as I recall. But that's 8 tests. You know, and if you look at the data, let me go back to that screen for a second. If we look at this data, you can see quickly why what I've said in the past, which is a single test is worthless. Have a look at it. I've got numbers ranging from 6.42 to 7.29. That's not atypical or abnormal for this sort of testing with equipment that's this sensitive. You can get that kind of spread in your data. And the more of these tests that we run, the more accurate the final result will be, or at least the more accurate it should be. This really shouldn't get worse. It ought to get better. Now, I don't know. Who knows? Maybe it does get worse, but I think that's one thing a lot of people miss that haven't gone through this sort of stuff before. You can't just run out there and do a test and say, Eureka, whoopee, there's the number, I'm done. No, you ain't. You got a lot more work to do. So what I want to do, this is 8 tests with this particular torsion balance. I've got 8 in the books. I'm going to try to get that number up to 10 or 12, because really at the end of the day, I'd like to end up with at least 20 and maybe as many as 30 data points. And at that point, I think I'll feel like I've got enough information to be statistically valid. So
I like how it's written on the chart, where you've got the chart just on the side there.
yeah. Now, this is a spreadsheet that I use to, this is the very last test. You can see I don't know if you can see my cursor or not, that yellow line there, where it says G, over on the left side in that bigger table. That value is calculated by the spreadsheet. All I have to do is put in the resting points, east and west. And it will spit out quickly a gravitational constant for me. So let's see, let's go back to the camera view. Oh, goody. I see things are moving all over the place.
Where you've got resting point and east and west and the time, is that your time, just so you know by the clock that's on the experiment?
Yeah. I'm trying to keep a timestamp on it. Hopefully, I've got all this captured on video, either on YouTube. In fact, I started a live stream yesterday, which was unlisted Uh,
Yeah, I watched a bit of it.
yeah, and I just let it run. In fact, I just turned that live stream off a few minutes ago. And so there's 12 hours of this sitting there. And eventually I'll publish, make those, either make them public or at least publish a link to them. So everybody go back and back check what I'm doing if you want to take the time to do all of that. Documenting all this stuff becomes a pain in the ass.
So, in actual fact, with the videoing of the experiment to this point now, somebody else out there could be sitting down doing what you're doing with all the numbers and writing out their own spreadsheets, taking all the data points,
Yep.
and coming up with their own version of the spreadsheet data that you've got.
Yeah, absolutely. If you want to do your own calcs, feel free. I'll make every bit of the information available. I think I already have, but all the details about the device itself and, measurements and masses and all that stuff.
Phil might have some spare time on his hands.
I would imagine. I would imagine that Phil's got better things to do than play with these damn numbers.
Now we've got a Brian dropped in.
Yeah, Don Giza. There's a lot of video on my channel about Cavendish. I really need to put all that stuff in a playlist, get it separated from everything else, all the debunking stuff. But yeah, I think I covered pretty much everything I did fairly thoroughly as I was building all this stuff. There's quite a few.
Well, look at all the objections that you've had for the experiment, and you look at that and you go, well, those objections are not really warranted because of what you've got now for what you've done for the experiment. They're just unrealistic, the things that they've said for the variables.
No, I don't think they are.
Like even with the electrical magnetic field or something, whatever that one is, electrostatic, I think it is.
Well, yeah, you can talk about electrostatic influence, and I absolutely was able to see some of that happen. But that prompted me to take some action, which I initially avoided doing just because I was getting tired of messing with it, and I wanted to get on with doing some testing. But I took the whole thing apart and completely wallpapered the inside of it with copper foil to eliminate any possibility that electrostatic charge was having an influence on it. I put a 8-foot ground rod 20 feet away from this thing out in the dirt out there, so that it's not just connected to ground in my house electrical system. It's actually connected to its own dedicated ground rod. And so I've got one ground that runs in from point to point to point with no loops in it, which is something you always need to watch out for with grounding systems. Don't build ground loops in anything. In other words, don't ground both ends of it. It's not a good idea. Oop, who joins?
Me.
Yeah, there's Brian.
Yeah, hey, Brian.
Look, has it moved back to the central position?
No,
Because
no.
I've got it here at 9 minutes 33, reading 190 mil, and
Yeah.
now it's reading like 230 mil.
Yeah, that's what it started at about 238, and then I moved them.
Along,
Okay.
yeah.
And it was very very stable and very steady.
I've gone up and down on the slider on the YouTube. I've paused it. I've gone up and down on it, and after I've seen you walk around and reset it there, and the ball we're looking at now is on the right hand side as we're looking at it.
Yeah, that is correct.
I can sort of see the red line moving over there.
Yeah.
And it's 190 millimeters.
Yeah.
And now the ball's on the same side, and it's come right back to virtually the central position.
Yeah, it's oscillating is what it's doing. Yeah, this is the oscillation that you see. This thing is a horizontal pendulum. Okay.
Oh, it's gone back up again now.
Yeah, it's going to oscillate back and forth like this. But each time
is there no dampening on it?
Well, there's the only damping.
You've got no damping on it.
Yeah, the only damping that's in it is just what very little bit of air resistance would be presented by those little lead balls inside that case that are moving so slowly. So there's not a lot of damping at all.
And the torsion wire is what it's the resistance, isn't it, Blue? The torsion wire is what?
Yeah, the torsion wire is what supplies the restoring force. In a normal pendulum, like a clock pendulum, gravity is the restoring force. You know, it's pulling the pendulum down. But in a torsion balance, the restoring force is not gravity. Gravity's going the wrong direction. Gravity's going down. You need a restoring force that goes sideways, and that happens to be the torque in the wire. When you twist the wire resists that. And it gives you the restoring force that pulls the balance back the opposite direction. But when you first disturb it, like I just did there 15 or 20 minutes ago, you get this enormous oscillation to begin with. And as we sit here and watch it, you'll see that each time it gets to be a little less and a little less and a little less. And once we get down to the point where the peak and the minimum is within, say, 6 or 8 millimeters of each other, you can feel pretty safe at that point, taking the average between those, the high and the low number, and saying that's where that's where the steady point's going to be. That's how we do it. That's how Cavendish did
it. Did he get the same oscillations then, did he?
Yeah, close. His oscillation period...
similar.
Yeah, somewhat. His oscillation period was, very nearly the same as what I've got here. That oscillation period is simply determined by, by the wire or the torsion element. In my case, in Cavendish's case, it's a piece of wire. It's just the characteristics of the wire. If I put a larger diameter wire in there, say I go from 0.007 diameter to 0.008, the oscillation period right now is about 15 minutes. If I go up 1/1000th of an inch in diameter, that period will go from, say, 15 minutes down to 12 minutes. And the larger I make it, the shorter the oscillation period will be. But for sensitivity's sake, you need that longer period. So there's a happy medium. You just got to experiment with it. And there's a happy medium that you can come to. The combination of the masses, the moment of inertia of the balance, and the characteristics of that wire that gets you in a range where you can make reasonably accurate measurements. So it's not an easy thing to come to, but I'm pretty happy because ahead of time I had calculated that I was going to use 0.008 wire, and the larger small balls. I've got the little ones in there right now. They're 330 grams a piece. I've got another torsion balance that's got 780 gram balls on it. And it actually works really well, almost exactly like I predicted. I say I predicted, exactly like the engineering calculations would tell you it would behave. So that's probably an advantage that Cavendish didn't have. I don't know that that engineering was that advanced in those days. Maybe it was, but
what's this blue? I don't know if it's a wire or a piece of string or something that I'm seeing to right of centre, just before where the big ball's hanging. Is that a piece of string or is that a bit of wire? Or
that's the ground wire.
Just that's your grounding wire, right?
Yeah, that's the grounding wire that's coming down from the top. Let me see if I can tilt this camera up a little bit.
Is it through a nail or something there? Is a nail supporting it or something there?
Well, let's see. Let me switch my view so I can see what I'm doing.
Yeah, it's on the horizontal rail just above you.
I'm going to tilt this up a little bit.
On the end.
You can see it'll take this a minute to catch up. Let's see, let me go back to, I'll sit over here for a second. Uh-oh, no data. Now we got data. Okay, now you see I'm going to tilt the camera up. Come on, tilt the damn camera up. Stop screwing around. There we go. There we go. If you look on the right hand side at the very top of the enclosure, you can see that wire connected to a ground lug up there, and then it runs across the beam, and it comes down the side over here where you were seeing it. But there's also a ground wire.
The small balls. Are the small balls hanging on wires, or are they attached to a beam then?
No, they're actually hanging on wires.
Can I see them wires?
Let me see.
You want me to post a pic in Discord for them, Blue?
Yeah, if you can, Terry. I don't have any of those pictures out here on this particular computer.
Yeah, they're all over. Yeah, you've got them all over in my. I'll just scroll up, see if I can find it. So you want the one with the wire? Okay. I think there is one showing it. Too far.
Should be.
Got the one with the enclosure. Yeah, got the one with the enclosure.
I can show you on camera. I think I'm not going to be able to see it from where I'm going to have to stand. But I've got the other torsion.
I'm sure there's
the other torsion balance over here. Let me see if I can hold up one end of it for you. Hang on.
Now the only one I've got is an empty frame. You can't see that. I think they're on video. I think a lot of the images.
It's just that I can't see any wires coming out of that wooden box that's supposed to have the smaller balls in.
Yeah, I know, that's the image I'm looking for, yeah.
Yeah, you don't see those. here's the wire.
Oh, you don't see it? That's why I can't see them then.
Yeah, here's the larger, the small balls. That little wire that's saying on this. 10,000.
Oh,
Here
is
you
that,
go.
that's what's inside the box, is it?
Yeah.
Yeah, I found an image. I found one. Yeah. I'll just post it in here. Might help. Be paste.
I'll be right back.
Where are we? We're in live chat, are we? In here? Live chat. That may help. Can you see that, Brian, in Discord?
Yes, I can do. Thank you very much.
Yeah. So that where the arrows are pointing to the significant components. The torsion wire comes down from the top down the central point down to the middle of the experiment through the little hole in the frame, and then down on and holds onto another wire that goes to one end of the torsion beam and goes to the other end of the torsion beam. And it's all pivoting on that one central wire that goes up to the top.
So that is perfectly balanced, is it?
Yeah.
That's pure balance. There's nothing else interfering with that.
No.
You've done a good job, mate. And I
Yeah.
take it it's in a box so it doesn't get interfered with wind or heat.
Yeah. Yeah, that's all sealed. That's completely
Yeah.
sealed, all that.
Yeah. The only suggestion I put to Blue was that because people obviously think there's a deception going on, I would try to make that out of something like Lexon or something that, they can see through. But, I mean, he's been open about it, so...
Yeah, the only open windows is on the ends and in the middle where the laser is. That's the only sections that's actually open.
Yeah, I've been.
And what he's measuring is the twist in this vertical wire when the balls get attracted to the mass.
That's exactly right. That is exactly what we're measuring.
Showed that for you out on the YouTube for you, believe it or not. I haven't got a control of you.
Yeah, you've made a good job of it, mate. If you've made that yourself, it is a real nice bit of carpentry, that is.
Oh, it is.
There's a lot of video on my channel. I documented pretty much every step of this and how it was built.
Brian, are you in my Discord?
I don't know. Who are you?
That's Terry Davies.
I'm in whoever sent the link. I think it was Blue sent me a link.
I'm in the Aussie Perspective. Blue's got a specific channel in there that everything's posted from way to go, from the construction and everything of it. I'll send you the link to my, because that way it's all wrapped up in one easy to Okay, where am I? There you go. You'll find Blue over on my channel now and again.
I mean, I sit on the other side of the fence, don't forget. But I'm always, I'm a hands-on guy myself. I build race cars for a living. So I can appreciate anybody's input like this and their effort they've put into it. What it's proving, I don't know. It's proving for me that lead attracts lead. That's all it's proving for me. What we need to do is change these materials to different materials and see if we get the same effect.
We're going to do that too.
It's not my test. It's Blue's test. So
we're going to do that for fun, not to try to get any actual data, in terms of the gravitational constant, but just to demonstrate that it doesn't matter what you use for the mass, as long as it's not magnetic.
No, obviously not. But you see your little balls hanging down here. they're hanging down because of what?
That was the way Cavendish built it, and I think what he was thinking is that he was going to put them in the smallest little confined area that he could put them in to eliminate any as much as possible convective air currents that might form if you change the temperature rapidly of that wooden enclosure. And that had to be something that he was concerned about. I mean, he was living in England in 1798 and doing this way before there was any such thing as any air conditioning or heating systems. So this was totally at the mercy of whatever the weather was doing. And like anything, I mean, if we heat this case up, one side of the case, for instance, either side of the case for that matter, then the air, there's a thermal resistance. It takes time for that heat to make its way to the inside, and then the whether you've raised or lowered the temperature of the case relative to the air that's inside it, you're going to either take heat away from the air that's in there or add heat to the air that's in there through conduction right at the surface where the interface is, where the atmosphere that's inside there is in contact with the case. But then that will set up a convective air current. If the air is warmer, it's going to try to rise inside the case, and then as it goes up, it cools off and drops down. Works like an old Model T Ford radiator, actually. Cooling system on a Model T, same sort of thing. So that's what he was trying to get away from, is anything that would generate air currents inside. That really could be, and probably would be, by far the largest source of error, systematic error in this whole thing. If we just had those small balls out here in this room, where me walking around or opening a door or my little window air conditioner that I use here to control the atmosphere here in the garage, if anything like that were to happen, then you're certainly going to very easily cause that very sensitive torsion balance to move. So that's the whole idea. You got to protect it. And that case is it's airtight. The way I put it, it's airtight. It doesn't mean it'll hold pressure. It will not. And I've left a couple of very tiny cracks up at the top of it, just so that I don't want it totally sealed.
Well, surely the wire that goes through the top of it, isn't that?
Huh?
The wire that beam's supported on must pass through the top plate, mustn't it?
Yeah, it passes through that top plate, but that's well sealed up there.
That's where an interference fit, surely. You didn't make that exact size to the wire.
Oh, you'll have to look at that mechanism that's up there on the top. That's quite elaborate. It gives me a way to adjust, to turn that wire slightly and adjust it to center the balance. If you don't have that ability, you can't make this thing work. You've got to have a way to make the adjustment. Well, that's a pretty elaborate little gizmo up there, and a fellow over on your side of the pond, two left thumbs. I call him Lefty. Just did a marvelous job on in fabricating that thing I designed, and then he improved it quite a bit with some of his engineering expertise. Terry, if you can find a picture of that.
Yeah, they're all over in my Discord. I don't know if there's another one of that, or that's showing it in situ, so that's that one.
Yeah, it doesn't
Well,
have any.
not fun.
It doesn't have any O-ring seals in it or any such as that. Like I say, I don't want the thing to be pressure tight. I don't want. I want it
No,
to
there's
stay. I want it to remain at atmospheric pressure. As the barometric pressure changes a little bit, you want the thing to be able to breathe, so to speak, but to be as protected from wind or any airflow as you can have it. And I think we've got a pretty good compromise here. I mean, you can't notice any movement just because air is moving around inside here. You don't see the balance do anything. So I'm confident that we did a pretty good job on that part of the engineering of this thing.
I think that's the same. Yeah, there it is. That one.
What's this? Some sort of adjusting mechanism, is it?
I could explain it if Blue's not.
Yeah, I can't see.
Adjusts,
Yeah, why don't you?
the adjustment mechanism for the torsion wire.
Yeah, go ahead and explain
Very
it, Terry.
fine.
It adjusts. You can say it adjusts left and right adjustments of the torsion wire as it comes down onto that torsion beam for the oscillation for left and right. So you center it by turning the grub screw minutely. It's very sensitive, the amount of ratio of the turn, and that'll help you center the oscillation to zero it.
Yeah, get it set to
Pretty
zero.
well close.
What's that about? 0.75 the thread pitch.
Oh, I don't know what it is. Very fine. It's a very fine thread. It takes a lot of turns. I have to turn that little knob out there probably, at least 50 full revolutions to get that thing, more than that, maybe 100 revolutions to get it to do 360. But you need that kind of very fine adjustment, because you're only moving this thing, oh geez, tiny fractions of a degree to make it center, to get it to center. So the way you start is by putting those big balls, the big lead balls, not in the position they're in now. Rotate them 90 degrees where they're equidistant away from both ends of this thing, so they're not having any effect. And then let the torsion balance settle down. And when it settles down, then you make the adjustments up there until you get the thing to read zero. When I say zero, I'm talking about zero on that scale that you see in there on the lower right-hand corner. You're actually looking inside the box, and that upper scale is screwed to the very end of the torsion balance. Screwed to the very end of that wooden beam. It's really hard to get it to be exactly zero. I just try to get it within a 0.05 inches of zero, and I'm happy. That's close enough. A couple of times I've gotten lucky and got it to be exactly right, but it takes too much damn
What's the laser
time.
reflecting off then? What's diverting the laser?
I've got a front surface, or some people call it a first surface mirror, that is mounted right on the center line of that wooden spreader bar. That's not really a torsion beam, it's just a spreader bar is what it amounts to. So the mirror is sitting right there, right on the center line, and the laser hits right on the center of the mirror. So as the mirror turns, of course, you get the reflection off it. And that's great, because it doubles, if the torsion balance rotates 1 degree, then the laser dot moves 2 degrees. You get an automatic doubling of the of the movement of the laser. But I've got to. But you also multiply all of that by the distance away from the mirror that the target is.
Yeah.
So altogether,
Yeah, because the arc would increase, wouldn't it?
Yeah, altogether, it's written up there at the top. The actual move, every time the beam moves 1 millimeter, the laser dot moves 10.25 millimeters.
Oh, right. So 10 to 1.
Yep. So a little better than 10 to 1. But still, if I had to, I could read that vernier scale there and get a very accurate reading.
The problem for me, it's drifting so much. I mean,
Well,
it's so sensitive, it's picking up road, cars going past or lorries going past.
Nah, it won't do that.
It won't.
No, it won't do that. I don't even bother it as long as I stay 8 feet or so away from it, or I'm just right off the end of it. It's only when I get within 2 or 3 feet of it that the mass of my body starts to have an effect on it. Remember, it's the square of the distance. So every time I double my distance, yeah, you get
That's
one.
what I was saying to you before, wasn't it? About don't put them balls right up to it and see if there's a sort of a break off point where the mass doesn't affect it at all.
Yeah, I want to do that too before it's over with. Right now, I want to get an accurate, or as accurate as I can make, a measurement of the gravitational constant. So we're just going to keep doing what we're doing for a little while, and I'm going to change that balance out to the larger balls.
So, what is the distance between the balls now? Halfway between that box and the edge of the box, or not, how big are the balls inside?
The balls inside are 1.5 inches in diameter. But you don't really care what the diameter is. The question is, what is the center to center distance? How far is it from the center line of the big ball to the center line of the little one? That's the distance.
But you still need an air gap. You need an air gap.
Oh yeah,
don't you? I mean.
Yep. The let me give it to you. Let me give it to you in millimeters.
It's what? Sorry.
Right now.
At 20 mil.
Right now, the little
more than 20 mil.
Right now, the big balls are sitting about 4 millimeters away from the case. That's as close as I dare get it, because I don't want to accidentally have them bump into the case. If they do, then it upsets everything for an hour or two.
Yeah.
But the distance between the centers of the balls is 5 3/4 of an inch, which is what? 146 millimeters, center to center.
Yeah. Well,
very, very similar, if not very similar, if not identical to what Cavendish used. I did the best I could, given the information I had, to duplicate what Cavendish had done, with one exception. His torsion balance, I should say. I don't like calling it a torsion beam because that's not what it is. The torsion balance he used was 6 feet long, I didn't have enough room in here for that. I don't have enough head height to be able to put this thing together. So I cut that down from 6 feet to 4 feet. But the size of those chambers that the little balls are hanging in are exactly what Cavendish said he had. So the width of this case is exactly what Cavendish said he used. Fair dues, I didn't have a set of proper, like engineering drawings to duplicate Cavendish's work. I had to do the best I could with the information I had. But I think it's very, very close.
But his balance bar then being longer would basically gear the thing down compared to what you're getting, yeah? Is that
Yeah,
how I
yeah.
understand it?
Yeah.
Yeah.
Well, the same amount. Think of it like a torque wrench, right?
Yeah.
It's
yeah.
like
further you hold it.
Yeah, I've got a shorter torque wrench than he had, so I've got to be able to pull on the balance a little harder than he pulled on his to get the same amount of deflection. It's an interesting engineering challenge. It really is. So let's see. Let me go back and swap views again. For those who have joined, let's see. I'll give this a second or two because they're hearing us live. But the video lags behind just because of OBS, the way the thing is set. But I want to show these results again for the people that have joined since we did it the first time. With this particular torsion balance, I have run to date 8 tests that are legitimate tests. By legitimate, I mean didn't have something funny happen, like had to open the garage door or do something like that upsets things. So now we can see if you look at that little table on the right hand side, you'll see a column that's got 8 black numbers and 1 red number at the bottom. The red number at the bottom is the average of the gravitational constant that we've measured so far, and that is 6.655 times 10 to the minus 11th. The actual accepted number is 6.67 something or the other. These measurements right now average to within 0.3% of the actual value of G. And that's pretty, well, actually, that's pretty damn lucky is what it is. I hope it stays like that.
That column has just got way too many 6s.
Didn't think about that.
You know the alleged speed we're going.
Oh, yeah. Yeah. I think we can find enough 6s there to make that number too, can't we? But as I was pointing out earlier, and Terry and I were talking, you look and you'll see numbers that range from 6.42 or 6.24 up to 7.29. This shows you why no single test is legitimate in any sense of the word. If you only ran this thing one time, you would have no idea what you had. And even 8 of these tests are not enough. That's not statistically valid. I need to run this 20 to 30 times to have a good feeling about the accuracy of the data. So that's where we're headed. I'm going to try to run it. Yep. Yep. And then we can analyze the standard deviation and all of that good stuff.
orientated east to west, north to south, or is it just randomly?
Now it's actually oriented right now. As you look at it, let me put the camera view back up. As you look at it on the screen, what you're seeing, we're on the east end of the experiment. So north is to our right, south is to our left, and we're facing west.
You're thinking, yes, magnetic field is going to affect the experiment in some way.
Well, you have to take all the variants into your thinking, don't you? I mean, we definitely have a magnetic field, don't we? There's no arguing about that. You have to take all these, and of course, there's the spin of the Earth. The Earth's spinning at 15 degrees an hour, east to west, from west to east. So you have to take that into your calculations.
Let me shout out to JSS Tiger for a $5 super chat. Thank you so much. And super chat says, mail a signed copy of your report to Quantum Eraser's doorstep. I somehow don't think Quantum Eraser would pay much attention to it, really. But it would be fun. And to Feral Cat and Judy Bassett in the chat, you're certainly welcome. I hope you guys can have half as much fun looking at this stuff as I've had doing it over the past, what has it been now, 6 or 8 months.
If you see that thing I've just posted in the chat there, that's they got pissed off with theirs and they literally cut it up into bits. They could never get it working.
Yeah, I've seen that. I've seen that. Yeah, I've seen that very video several times, and it makes absolutely it makes no sense. I don't know why they would have cut the. What's cut off has nothing. It's just the mounting foot. That's all. I don't know what good it would have done them to cut that damn thing off that way. Wish I could show that. Maybe if you've got a link to it, post it out in the YouTube chat.
I mean, this story I'd heard was that nobody could get onto work like Cavendish did, or allegedly did. But
well,
it looks like you cracked it.
I'll tell you, here's the deal. That device that guy's holding is, and talking about cutting apart and all of that bullshit, that thing is made by a company named Pasco, P-A-S-C-O. You can Google them, Google Pasco Cavendish experiment, and you can see that thing, and you can purchase one from them. Now, they tell you that straight out of the box, its accuracy is good within 20%, I think. And then doing some other condition, I forget how they've got it broken down. But I remember that if you go to the trouble of using acceleration measurements, which is very hard to do, if you do acceleration measurements, the best they guarantee is accuracy to within 5%. But it's a tiny little thing. You see the size of it. So, they don't expect you to get exact dead-on numbers like Cavendish got. Well, he wasn't dead on either. He got within about 1%. I'm just sitting here reading the chat. Glenn Collins and Professor Phil talking about rotating this thing, and I've thought about that. And I don't know that I want to even try it because of just the physical constraints I have here in the garage. If I turn this 90 degrees, it's going to make it really hard for me to find a place to put the target. I'd love to be able to do that.
Yeah, that would be.
I really would. Some of these, some very sophisticated versions of Cavendish that are done in a vacuum and all of that stuff are actually done on a precise, the experiment is placed on a very precise turntable that rotates very slowly so that it's continually reorienting itself. But now you're talking about people that have, lots and lots of money to spend on doing these things. I got to do what I can do with a few $1,000 here in my garage.
Are we saying the balance beam is running east to west?
Yeah.
Right.
Yeah, exactly.
I would expect, I don't know what you think, if it was orientated north to south, you would get more of an effect if the Earth spin was affecting it. You would see that more, wouldn't you, north to south?
Yeah, you would. But there's no reason for it to know anything about the spin of the Earth. Really shouldn't make any, it won't make any difference.
Oh, it wouldn't. You get the same deflection whether you put this ball on the right or the other one on the left. Do you get the same average deflection?
Yeah. It doesn't change anything.
But if Earth spin was an element, then you're going with the spin if you're running east to west.
You're right.
So you wouldn't really expect to see anything. I'd have thought if Earth spin did affect it, it would show up more if it was orientated north to south.
Yeah, if that were going to have an effect on it, it would be much more pronounced if it's oriented north and south, just because the little ball on the north end would be going a little bit slower than the little ball on the south end, right?
Yeah.
But that difference over 4 feet is so minute, you'd never see it. What's the red dot doing? Anything?
No, not at the minute. About 20.8 20.7.
Starting to settle down a little bit.
Yeah, it is.
Let's see, I'm looking at it live. It's sitting on about 205. Have to go back and try to replay it. I don't think this. I think I can do this without messing up the stream.
You just walking into that area could fuck it all up, basically.
Yeah. Yeah.
You need to be able to move these balls then remotely, don't you, somehow?
Well, it has something to do with how long you're in there too. So I don't spend any time over there messing around. When I go to move the balls, I move them and get the hell away from it. Another shout out to Judy Bassett, €7. Thank you so much, Judy. I really appreciate it. What I try to do, Brian, what I've had success with is setting the balls in one position or the other, and then getting the hell out of here. And I just run the live stream unlisted, and I can go in my office and sit and watch this thing and not be out here around it. And I feel best about the test that I do in that condition.
Yeah.
Can't avoid being around it a little bit, but as long as I don't hang around for 10 minutes or something, it usually only takes me about 60 seconds to walk around there and make that movement and then get out.
I'll tell you another thing you can do is basically take the lead ball, these big lead balls off completely and just move the bar.
Yeah, I've done that.
Oh, you have?
Yeah, I've done that.
As like a blind test, if you like, and
Yeah.
see if there's any input of moving this torsion bar for the bigger balls.
Yep.
See if that has any effect.
Yep.
Or put dummy weight or balloons or something on your very small mass.
That's why you put the big balls at 90 degrees in the middle when you're doing a neutral test.
Yeah.
Yeah, but I mean, just moving. I mean, I presume they're pivoted on another bar at the top here, are they?
Yeah, they are.
Sort of pivoting. Yeah.
Yeah,
It's just to eliminate things, isn't it?
It's sitting on a cross beam. There's pictures of all this stuff on my channel, but it's the upper bar, the bar that rotates that these lead weights are hanging off of, is sitting on top of a thrust bearing, and the shaft at that thrust bearing is in another beam that's fixed to the framework here. And then I've got a little pulley up there.
And the cable that the small balls are hanging off, are they parallel? Are they in the center line of that out of the bigger ball?
Yeah.
Well, the center line.
Yeah.
Yeah.
Yeah, I took a lot of care to be sure that I had that thing that way.
Yeah.
The actual distance, the little balls, center to center, are 48 inches. That's, what is that, 48 times 25.4. 1.219 meters, center to center. The big balls, that that beam up there at the top that rotates. I forget what the number is, but it's a longer distance than 1.219. There's a reason for that. I wanted the big balls. This is a mistake that Cavendish mentioned that he made when he built his. He forgot that you're not rotating a full, 180 degrees. So if I made the big balls exactly 48 inches apart, like the little ones are, then they're not in line with the little balls when they come into that resting position. So that was something I laid that all out and made sure that when they come to their rest point, they're directly opposite the little balls. That's where you want them. Exactly perpendicular to the center line of that balance beam. There's a lot of little subtle details to this thing. I forget about a lot of it. But as I go back through and start writing this up in the form of a final report, I'm going to try to remember all this stuff.
What's that saying? The devil's in the detail?
It is. It really is.
I see a Mr. Allen and a Mr. George dropped in.
Hello to Rob Barton there in the chat. There we go. Hello, Alan Evans. Hello, George.
Good afternoon, Blue, or morning, or whatever.
Yeah.
So what's going on here? I just received a notification via email that I was put on the server.
I'm going to have to turn George up. He's not using a microphone.
Let me go get my headset. I'm having a hard time hearing. I'll be back in a second.
I just turned him up. Yeah. Go again, George.
Yeah, I've got George all the way up.
Yeah, I got him up on my end.
I didn't have my plugged in.
That's worse.
Uh-oh.
Okay. All right. Good evening.
Yeah, you got something wrong up with your end, George.
He's on his other laptop, I bet, or his iPad.
Yeah.
His mic is absolutely crap on it. Oh, well, it's getting on towards 3 o'clock here in the morning, so I better get some Zeds.
Okay.
Good luck with your observations.
Well, thank you, sir. Hey, thanks for dropping in.
That's you good people.
Thanks for dropping in, Brian. I appreciate you coming. Good chat tonight.
Thanks a lot. Yeah.
We can scream at we'll scream at each other again over on Jose's tomorrow. How's that?
Yeah. Yeah. Take care.
Okay. What have you been up to, Alan?
Oh, had rather a good day. My daughter delivered me my new grandchild this morning.
Oh, congratulations.
Little Harriet. Not sure exactly what time she was born, but she was 10 pounds 4 ounces.
Good God.
Born by C-section, so not quite as dramatic as the weight might suggest, and she was still a couple of weeks early.
Well, both of mine were C-sections. The first was an emergency C-section, which was maybe one of the more, probably the most terrifying thing I ever went through.
Yeah, I had exactly the same thing with my three. Emergency C-section for the first one, and then planned for the second two.
Yeah, when we got pregnant with our youngest daughter, the doctor said, "Well, there's no real reason why you can't go ahead and have a normal vaginal birth." And I said, "Yeah, there is a good reason why. You try that, and I'll choke you. We're not going through that shit again. It's going to be a C-section. Period. End. No discussion." And he said, "Oh, okay, fine." And that was really good. That was like baby by appointment, you know.
Yeah, that's pretty much what Rosie had this morning, baby by appointment.
Yeah, be here at 5 a.m. By 7 o'clock, we had a baby. Mom back in the room, feeling well. Oh, yeah.
Which is also, of course, why I might be in the same time zone as Brian, but I'm kind of not really very sleepy right at the minute. I'm still a bit buzzed.
Oh, if it was Monday, we could have done a live stream.
That was Tuesday. It was Tuesday. So yeah. So Rosie's oldest was born on the 1st of the 2nd, 20, and then his sister was born on the 2nd of the 3rd, 21.
Yeah, shout out to Colin Ellicott in the chat. Also JH. And Rob Barton says, "The devil is always in the detail when it comes to science." You're absolutely right, sir.
Yeah, that's a delayed agreement.
Absolutely.
Right.
It's
Better.
oops. Was that you, George?
Yeah, I wonder.
Yeah, I can't slide this bar any further off the screen. It's as far as it'll go.
I don't.
Turn my speakers up. I'll just have to flip the mic
Okay.
off.
Yeah, I can't turn him up any further. I've maxed it out on my end.
Same here.
If you're saying anything important, George, we'll just nod our head.
Okay. 7.
Hello, John Rapp. And Doofus Manford, how are you today? For the second or third time, I think. Rob Barton says when Blues paper comes out, there'll be a lot of flurf derp. There already is a lot of flurf derp. Those fools have been losing their mind. They are absolutely pissed about this.
Yeah, well, I haven't heard anything new yet.
The problem is it's very, very hard for them to deny it when they can see it happening live on YouTube.
Oh, what happened to your toilet paper, Blue?
I took it off. There we go. I'm going to turn you down a little bit, Terry.
Yeah, you're humming through on mine now when you're talking.
I don't know what's up with that.
So you've lined the inside of the torsion balance case with copper foil?
Yeah. It's stuff that's made for this purpose. It's got conductive adhesive backing on it.
So you've basically turned it into a Faraday cage.
Yeah.
Yeah, pretty much.
So nobody's electric fields are going to be getting in there, are they?
No, sir.
Well, we're just discussing the north-south orientation of the device in case the Earth's magnetic field had any influence.
Hey guys, it's any different?
A little better, I think. Was that you, George?
Yeah, I don't know what's happening here. Everything's gone to hell ever since I upgraded the laptop Windows 10.
You're sounding good now.
Oh, okay.
I got you at 200%, George.
All right. I still don't understand. Level's still low.
That's all in your Windows settings.
Well, we can find today. Go into Windows.
So you go through Device Manager and just check in there. You might have something turned off, on, or it should be off or something.
Well, it did do an update the other day. So something.
Yeah, that'll do it. I had an update that screwed with me banana one time.
I've had that happen too.
Yeah, I heard the comments on the magnetic fields, although quite how you're going to be affecting a non-ferromagnetic metal with the Earth's essentially static magnetic fields, I'm not really sure.
Oh, the Earth's magnetic field is far too weak to have any effect on this.
Well, just look how much it takes for just a little compass to even be affected by the magnetic field.
mean, you've got to put a decently good bearing surface under a compass to get it to spin properly. And that's not just with a magnetic needle. A needle that is ferromagnetic. It's with an actual damn magnet for a needle.
Yeah. Well, there's no ferromagnetic material here. All the fasteners are brass. The hanger rods are brass. The balls are lead.
Has anyone complained about the electrical field in your garage with all the lights and power running through it, wiring and all that sort of stuff?
I haven't heard that yet, but I'm sure I will before it's over.
I haven't heard that one. Oh, what about the Rio in your concrete? You got Rio in your concrete, or is it just
No,
concrete?
it's just concrete.
Okay, oh, that cancels that one out too.
As evidenced by the cracks in it, there's no damn wire or rebar or anything else in there. That's pretty normal for here in the States. Unless you
Oh,
get...
the vibration of a truck going past. You haven't. The only way you could show that not to be the case is if you get your sledgehammer and film yourself banging the concrete somewhere near the experiment with the camera on it to see if there's any vibrational transfers through to it.
Is
Anyone wanted to show that one?
I just fiddled with a few. Things. Does this help or not?
Yeah, that's much better, George.
I can't turn you down though, but it's better.
Okay. Well, anyway, Blue, I was reviewing your Cavendish construction here, the apparatus, and I must tell you, from engineer to engineer, I'm really quite disappointed with your apparatus here. I don't know how you expect this to compare at all with strapping a banana and orange on the end of a construction level suspended by a spring from a cord from a step ladder.
Oh. Oh.
Yeah, that was a clear oversight on my part. Huh?
Was that a ripened banana or an unripened banana?
Well, I'm sure that would make a difference, and probably which type of banana you used. I mean, there are many different varieties, so. But, you might have to consult with the flat earthers on that one.
George, there is only one type of banana that you could possibly use for this. The Cavendish.
Of course.
Yeah.
Of course. It must be Cavendish.
Well, you know the Flat Earth Banana Factory went out of business because they threw away all the curved ones. That was meant to be funny.
I still think the best apparatus out there was the one about a year ago from a flat earther that did just that and had his banana and orange attached to the end of a carpenter's level with masking tape.
Almost as good as Chris Berry with his trailer hitches and kettle weights.
Oh my, I missed that one.
It's ugly. John Rapp in the chat wants to know if the grounding wire is on Q or closer to E. And for those of you that don't know what John's talking about, I decided I would name the little balls Q and E.
Yeah.
So,
I think that would be more appropriately attached to a couple of rotten bananas.
of course, the really big balls are named big and blue. But it's only fair that the little balls be Q and E.
Yeah. So at the moment, are we intimately looking at blue or big?
I've lost track. I forget which one's which.
Fair enough.
Maybe I should put some stickers on these things so I can keep their names straight. Hopefully we'll get some usable data out of this that we're doing tonight. Sometimes you have to just throw the test out when things happen. At times I don't have any choice. I have to open the garage door or something like that. And when you move that great big garage door up, it messes things up.
What you need is an airlock.
Yeah. But everything's pretty stable tonight. I think maybe we'll get some decent data. I've got 8 good tests. Probably more than that if I went back and looked at some of the earlier stuff. But I've got 8 good tests with these smaller masses, this lighter weight torsion balance. So I'm just going to keep running these until I get a dozen or 15 acceptable tests. And then I'm going to change it out to the other torsion balance that has the larger balls. And we'll do some testing with that. Should get the same numbers, right?
Oh, you should get at least close to the same results. Yes.
Yeah. Let's see if I can look at these oscillations a little bit. Looks like something like 205 up to maybe 216, 217. I'm looking at it on the on the YouTube studio, so I've just got a little tiny view. So that'd be something, an average of about 210. And the starting point was 238, so that would be 27 and a half, 28 millimeters deflection. And I know from the calculations that that is almost dead on top of 6.67 times 10 to the minus 11th.
This lift master that you have mounted to the ceiling, is that your garage door opener, or is that some sort of an electric winch?
That's a garage door opener. I know it's probably hard to tell from the video, but I made sure when I positioned this thing that damn thing is sitting centered up on the Cavendish. So its mass is not, well, it's equidistant from the two small balls. Although these uneven distributions of mass in and around the shop don't really have any significant effect on anything as long as you don't move them around.
Blue, I heard something earlier today. I wasn't paying close attention, but someone was asking about the density of the balls and and why you use lead and rather than something else. And I think the right answer for that is that the denser the material you use for the balls, the closer you can put them together for a reasonably sized mass.
Right.
Given the fact that, you know, the gravitational forces of attraction dissipate by 1 over r squared every little bit, you can get them closer together. The more sensitive or your apparatus becomes.
Yep, that's exactly right. You know, if Cavendish made any errors in judgment, the one thing that he did that I don't think he needed to do, Reverend John Michelle is the one that conceived this thing, of course. And Reverend Michelle had intended that the large masses be, if memory serves me correctly, 110 pounds, something like that. And when Cavendish got his hands on it, he wanted to make some changes to the apparatus. And one of the big change he made was he increased those large balls from 110 pounds to 340 pounds. Now that's pretty impressive, right? Well, let me tell you what that means. These balls, these 50 pounders that I've got hanging on this thing right now, are 6 inches in diameter. If I make them 12 inches in diameter, then they weigh 350 pounds apiece. And you think, oh great, I can get a lot more force if I do that, but not really, because it moves the center of that mass 3 inches further away from the little balls. And at the end of the day, what happens is I get about 45% as much force as Cavendish got, even though the big balls that I'm using are 1/7 of the mass of the ones he used. So yeah, that answer is the right one, George.
Yeah, well, I mean, for spherical shapes, the volume goes as the cube
Right.
of the distance out from the center, and the force drops off as a 1 over r squared. So your improvement is really only a linear function.
Yep.
In what I mean, the improvement is a linear function when you go to a larger size ball. So you're not really gaining that much
No.
by going to much larger balls for a given density.
Yeah, ideally we would use depleted uranium or gold or
Yeah, I'd go with depleted uranium or try to get a GoFundMe to buy enough gold.
yeah. Yeah, that would have been perfect, wouldn't it?
Oh yeah, yeah. I mean, it'd make the effort all that much more worthwhile.
But lead is just such an ideal material to work with. It's soft. It's got a low melting point. I mean, you could use something like tungsten, but the problem with that is you got to get that crap to 5,000 degrees to melt it. You can melt lead on the kitchen stove.
Yeah.
Um,
Yeah, the only problem is lead is 1/2 the density of, say, gold or tungsten and osmium.
Yeah.
And depleted uranium. Those four, gold, depleted uranium, osmium, and tungsten, they're all pretty much the same density. Only differ by a few grams, by about a gram per cubic centimeter, whereas the average is upwards of about 20 grams per cubic centimeter for those elements, and lead is around 11 grams.
Yeah, 11 something, something like that. If we, but I got 100 pounds of lead here that cost shipping and everything, $350 or $400, I think. Yeah, we could do it with gold for 350 or 400,000 bucks.
Yeah.
We could do it with tungsten if you have a weight.
I checked some prices a while back on depleted uranium, and it turns out that isn't much cheaper than gold itself.
It isn't. That's right. Tungsten, I suppose, would be a good bit cheaper, but certainly not $300 or $400 worth. Many thousands of dollars worth. And the problem of fabricating it, finding a foundry that could cast, tungsten. It's got the highest melting point of any metal.
Yeah, well, that's why it's been used for filaments in incandescent light bulb.
Yep.
And a really good job it makes of it too.
Rob Barton wants to know, is it sensitive to ground vibrations. No, it isn't. It is not. We're sitting on a 4-inch concrete pad here, at least 4 inches thick. I'm quite a ways, 75 feet anyway, away from the roadway, which is not heavily traveled. And I've not noticed any vibration from anything. Now, I can induce vibration in it by going over there and tapping that table it's sitting on, or tapping the enclosure. All I got to do is touch the enclosure, and you'll see the vibrations. But it's easy to recognize because what it does when you do vibrate it, the entire torsion balance swings like a pendulum then, like a vertical pendulum, not a horizontal one. And that changes the angle of the mirror. So what you'll see is the little red dot start jumping up and down as that beam swing, as the torsion balance swings back and forth. And you can see how steady it is. I haven't tried this. I'm, 6 feet away from it. I don't know what happens if I stomp on the floor. Can I do anything? Nope.
I said use a sledgehammer.
Oh, well, I have a sledgehammer somewhere. I'll wait. Mrs. Blue's Mrs. Blue's asleep in there. Sorry.
I was asking how much does the weight of the apparatus, is the weight of the whole apparatus, say at the contact of the floor? Where do you have it? A table with 4 legs there?
The table itself is pretty heavy. The table is the better part of 100 pounds. The apparatus itself is about 60 pounds. So I'd say 100, in the range of 150 to 175 pounds. I tried to.
So you're looking about 40 pounds on each leg then?
Yeah, something like that.
I'm assuming there's 4 legs.
Yeah. Just to be able to.
Vibration became a. Go ahead.
Just to be able to level this thing, I put little leveling feet. Well, on the big frame, the 4 legs of the great big frame, and the 4 little legs on the table. And the little leveling screws that I used have felt pads on the bottom of them. So that also helps vibration damping to a degree, I suppose. Inadvertently.
Well, vibration became a problem. One thing you could do is on the bottom of each leg is take like some well, with 40 pounds you could probably do might even be able to get away with dense wood like oak or something, but you could do it with metal, like aluminum metal machine cones out of a block of aluminum, and then you mount them on the bottoms of your table legs so that the apex, the tip of the cone, is pointed downward, and then you put steel plates on your concrete floor and have each of the legs touching the steel plates with the apex of the cone, and that will stop a lot of vibration from being transmitted up into the apparatus by having that point of contact being a sharp point with the floor.
Yeah. I'll tell you something else that about vibrations like that vibrations don't like making right angle turns. So if you put some outrigger sort of legs on it, so that the vibration from the floor would have to come up, make a right angle turn, and get into the leg, and then make another right angle turn.
Right.
That's pretty effective. We used to worry about this shit all the time with our mechanical wrapping systems in the electrostatic precipitators. Hell, I spent about 6 or 8 months of my R&D time doing vibration testing. We were trying to get we weren't trying to reduce it, we were trying to increase it, maximize it. That's more of an art than it is a science. I see Jason's back.
Yeah, well, I apologise for pointing him at your YouTube stream the other week. If I hadn't have done that, he wouldn't have known you existed.
Well, he's not allowed on the server anymore. Rob Barton's talking about vibration sheets. Yeah, you can buy those vibration pads. And they're fairly effective. They also make things, a gizmo that I remember we used at times for some applications called isomode pads, vibration dampers. You have to be careful though. Sometimes you do something that you think is going to reduce the vibration and it actually will amplify it. The best idea is to make shit really massive and heavy. That's the reason
Not very dense.
That's the reason in a chemistry laboratory you never ever see a precision balance, precision scale just sitting on a tabletop. They always sit on a seismic table, and it'll be a damn piece of rock 3 or 4 inches thick. But fortunately, I've not had any issue at all with vibration. Static was the only thing causing us any grief. And that's no longer an issue now that I've got everything shielded and the grounding system properly set up. I don't know that it matters much with static, but well, George, you know this from all your electrical work. The last thing in the world you want to do is build a ground loop. you can get some really funny shit happening when you get stuff grounded at two different places.
But I don't think it really matters in electrostatics.
I don't think it does either, but just to be sure, I made sure that everything is grounded at one end, but not both ends.
Yeah. Well, ground loops develop primarily because of the fact that you
Current flow.
open yourself up to magnetic pickup with changing magnetic fields, and that's dependent on loop area.
Right.
That's why you twist wires together, is to get rid of the loop area.
Yeah.
Well, that reduces magnetic pickup. And the only other problem that you have with ground loops is having to do with what's called common mode coupling.
Yeah.
And but these are all having to do with time varying electric and magnetic fields. In statics, it's just not going to matter because you can't have current flow.
Right.
And ground loops cause potential differences that can register as errors in your instrumentation because of current flow giving you different potential drops along the loop. And again, statics, the whole idea of statics is meaning no changes. Everything's static, so you have no current flow in electrostatics. So to cause potential differences, so I just don't think it's an issue. The important thing is to neutralize charges by taking each metal surface through a wire to a ground rod pounded into the earth.
Yep.
To bleed off excess charge.
Yeah, and I have that done very properly. I put an 8-foot ground rod about 20 feet from where I'm sitting right here, just outside the garage door, driven up and driven in the ground.
That'll do it. Sure, that'll do it.
Proper, regular. It's a copper plated steel rod, but the outside of it's copper.
Yeah, because any excess charge on any finite, reasonably sized surface, even having to do with areas of square miles, that's insignificant compared to the material of the Earth, the mass of the Earth, which is about 6 times 10 to the 24th kilograms. And so there's no chance of changing the charge distribution of the Earth with any excess charge you can have on a object the size of a bowling ball. And that's the important thing. You should just want to make sure the charges are neutralized. It wouldn't be sufficient just to connect everything with a wire to make sure that they're at the same potential, because even though things are at the same potential, you can still have fields and you can still have excess charges. You need to have that equipotential surface at the same potential as the Earth.
Yeah, I had everything grounded all along. But what I didn't think about at the time, the enclosure there has got four mounting points, and those are sitting on dowels that are doweled into that table. Okay. But the table itself is sitting on felt pads. So none of that wooden structure is in very close contact with the ground. Now there is contact up at the very top of it where the adjuster mechanism is. But I think what I ran into was some electrostatic charge building up on the wood case itself. And that's quite possible when you've got a fairly good insulator and this wood is dried out and it's got finish on it and all of that. That's quite possible to have happen. Cavendish had his 4 mounting points sitting on wood planks that were just driven into the ground. And I doubt he put any finish on anything, so the wood probably had enough moisture content. And it was directly into the dirt anyway, that kept him away from any problems. But with that bottom chamber now,
Well, that is all. Even if you had the surfaces lacquered and a real nice dielectric, where it's essentially a very good insulator, that is, of course, a potential problem because charge won't move or migrate and will just sit there. It's, basically bound charge.
yeah,
And the way you can get rid of that easily is there's a lot of products out there that are conductive sprays or liquids that you can coat the surface with to make it conductive. I mean, it doesn't have to be a good conductor. I mean, you could be on the order of many mega ohms per square, and that's good enough for charge to move and migrate and neutralize itself. In fact, that's how anti-static pads are built. You really don't want, like on your tabletop, when dealing with sensitive electronics, to use a metal tabletop unless you had that metal connected to ground, say through a mega ohm or 2 of resistance, because if you just take a metal tabletop and ground it to the earth and you have electrostatic charge, you will discharge onto that tabletop with extremely high current, which would damage your electronic if you're neutralizing yourself through the electronics to your tabletop. And that's why most electrostatic wristbands and anti-static mats and that are all connected to ground through a 1 mega ohm resistor, so that you limit that discharge current, so it won't take out your electronics when you say walk across the room and build up charge on you, and then touch things that are on a tabletop that's conductive, that your discharge won't be with a very large current that would damage your electronics. You want to bleed your charge off slowly. Oh, Blue.
whoops, I'm talking and got the mic turned off.
Oh.
Let me start over again. John Rapp asked about air displacement. He says they actually argued about it on Jose's. The entire reason that the torsion balance is in that wooden case is that wooden case isolates it from any air currents that are moving around out here in this room. That's the biggest failing that I've seen in so many of these amateurish attempts at building a Cavendish. You can't just hang that torsion balance out here in midair. Any slight air current, if you've built the balance and the torsion element sensitive enough to be able to make any measurements, the slightest air current is going to disturb the damn thing. But that wooden case that I've built is pretty well sealed. It's not pressure tight by any stretch, and I've intentionally left right up the very top some little tiny cracks, just so changes in barometric pressure can let things equalize. I don't want it to become pressurized or one way or the other. But I've got a little window air conditioner that runs out here, and there's airflow inside this garage from time to time, and you can see no effect of air current on the balance itself, none at all. I may take a floor fan actually and blow on this thing at some point, just to demonstrate that air movement is not having any effect.
Well, I was just thinking, Blue, instead of going through all the gyrations of trying to coat your surfaces, say with some sort of a conductive spray or coating, is what you could do to ensure that there isn't going to be any static buildup anywhere, is get yourself an air ionizer and just have an air ionizer blowing in your garage there to get rid of all excess charge in the air.
Yeah, that's possible. Well, you know, I've already gone through and totally lined the lower chamber of this thing with copper foil. So the area down there has a very good electrostatic shield in it. And it's the kind of copper foil that's got a conductive adhesive on the back of it.
Mm-hmm.
The stuff like they use in the electronic compartment in electric guitars and, you know, stuff like that. So right now it shows no evidence of any issues. And even on the table, I ran a piece of that copper foil right down the center of the table, right underneath the Cavendish, right under the enclosure. So I'm convinced that everything is in good shape electrostatically. And I don't really see any need to try to address electromagnetics. There's nothing magnetic in the system. Goodbye, Jason. So I don't know if you saw the measurements I made up to this point, George. Long story short, the average of eight tests to this point is 0.3% off from 6.67. That's just crazy good luck, I think.
Yeah, that's really quite amazing. I mean, when you figure that the best apparatuses that we have in the standards labs, like at NIST and over in France and a few other places, the best we've been able to determine big G is to 1 part in about 44,000. So that's what 1 part in 1,000 is a 1/10%. So you're off. Yeah, what?
1
By
part in
about
300.
200.
Yeah.
1 out of 200. So, no, that's really quite amazing. And that it does go to show how difficult it is to get a good grasp on Big G. As I said, even up to today, the best we've been able to do is 1 part out of 44,000, and that's pretty crude compared to all the other fundamental constants that we know.
Yeah, it actually is. I'm quite happy with the way it's working at the moment. I thought we could get close. I didn't know. I didn't plan on getting that close. And it may not hold. I mean, that's just 8 tests. So at the end of the day, maybe it's off by 1% or 2%. I don't know.
Well, the more data you get and look at the average and then the deviations out of average on each one of the individual tests will get you a pretty good handle on, whether you're really lucking out or you're really on the money.
Yeah, well, as with any sort of measurements like this, there's a spread in that data. Ranging from something like 6.2, 6.24 up to 7.2. That's high and low, But that's not surprising to me. I mean, you see this in this sort of testing.
Yeah, well, one of the interesting things about that, though, Blue, is this is why it's of such great interest in the standards labs and being constantly monitored, is we really don't know if Big G is really and truly a fundamental constant that doesn't change. There has been speculation that it does change over time, or it could change with position in the universe, and we really don't know. And that's why we're monitoring it as best we can and constantly comparing the value between, I believe there's 6 fundamental labs throughout the world that are doing this, and constantly, comparing their data to try to get a handle on whether or not Big G is truly a universal constant or does have some variations associated with it.
Of course, the guys that are doing that are doing it with equipment worth millions of dollars. So I'm sure they get a much tighter spread on their data than what I'm going to be able to get with a few $1,000s worth of equipment and parked out here in my garage.
Well, definitely. I mean, the precision resolution of your instrument pales in comparison with the very best out there.
Oh, yes.
And would not be able, probably, even if Big G changes, it's going to probably be down in the noise of what your apparatus would be capable of measuring.
Oh, yeah.
Now, at least that's what we think.
Yeah, it'd be out in the
Is
5th decimal place or something.
Interesting over time, and that's the interesting thing. Over time, we'll get a better handle on what the true nature of Big G is, and if it does indeed show some variations with position on Earth and over time. That has a huge implication.
Over here playing with my spreadsheet to see if I could.
But there's always, the possibility that some clever new young scientist, whatever, will come up with some new way of measuring big G than what we have today. Some fundamental new way of looking at it that would allow us to build more sensitive apparatus. There's always that possibility.
Yeah, there are other ways of doing it. Doesn't necessarily have to be like this, but it's fascinating to look back. You go back to National Bureau of Standards, built one of these things in a vacuum, by the way, and ran it for the first time in about 1930, and then they repeated it in 1942. I've got those test results, those reports, to remarkable accuracy even then. Without the benefit of today's modern electronics and stuff in terms of data collection. Those apparatuses were absolutely exquisite for the time period they were done in. And then you see other examples, more modern equipment, where they build their torsion balance so that the two small masses are not in the same plane. They stagger them vertically on a shaft so that you don't get as much influence, crosstalk, if you will, from one of the balls. Of course, you know what I'm talking about. This big ball here on this end is pulling on this little ball inside on this end, but it's also pulling on that far one too. That's a systematic error that you got to keep in mind and take into account. Doesn't make a lot of difference, but it does make some difference. And so they've done things like that staggered mass arrangement to help eliminate some of that sort of stuff. Whoops. Looks like we lost Terry and Alan. And it looks like we're down.
Well, it's pretty late for them.
Yeah, absolutely. And it looks like we're down to about a dozen people still out in YouTube watching us. I'm getting tired at this point.
Yeah, it's probably time to shut her down. It's 11 for you, 10 for me.
Yeah. I've been just taking cat naps for the last 24 hours. And going back and forth running this thing to get as much data as I can. Because it's behaving very well right now. Stability's pretty good. It drifts a little bit. I see the top end or the bottom end move 2 or 3 millimeters over a period of 8 or 10 hours. It just wanders around. I've come to expect that for whatever reason. I don't know why it does it, but it does it. can't really attribute it to anything. Cavendish talked about the same problem. It's hard to get it to ever just sit perfectly still. If you leave it alone for a period of a day, and I mean really leave it alone and don't go anywhere near it, it'll only move a millimeter one way or the other. But you got to be extremely careful. All it takes is me walking out here and getting close to it. If I get within 3 feet of it, 1 millimeter turns into 3 or 4 millimeters real fast.
Well, it's time to reduce your food intake.
There you go. That absolutely needs to be happening.
Yeah, you got to get yourself down to a pencil-thin frame. You're going to have a talk with that wife of yours.
Yeah. Yeah, she feeds me too well, that's for sure. Well, thanks for dropping in, George.
The thing that I find really interesting, having to do with the gravitational constant, big G, and masses and that, is, again, we don't say take the mass of the Earth. We don't know it any better than the precision with which we know big G.
Right.
Yet, the product we know very precisely. Like if you look at Kepler's laws, third law in particular, or anything having to do with orbital mechanics, big G times the mass of your orbiting, or of the central body in which you're orbiting, always comes into play. It's the product.
Right.
Big G times mass. Well, we give that a special name. It's called the standard gravitational parameter, mu. And given modern day satellites and orbiting probes that we've sent around the various planets, is we know it for most of the planets in the solar system, certainly the sun and the earth. We know the standard gravitational parameter out to 14 decimal places. Yet we only know big G, or the mass, out to about 4 decimal places on any of these bodies. And you go, well, gee, how can that be? How can knowing two numbers, not very precisely, when you take their products, you can know it to almost better than 10 orders of magnitude better than any of the individuals. And that's because of Kepler's third law and the orbiting satellites. We know the mass of the satellites precisely within our capabilities of, measuring to very small amounts of kilograms. And we can time the orbital parameters of these satellites very precisely, how long it takes to do one complete orbit, and we can measure the distance out from the center of the mass quite precisely with very precise optics. And so using Kepler's third law, we can get this standard gravitational parameter to, like I said, to 14 decimal places. And so knowing the product very precisely, we can, if we could know the mass of some standard planet, for example,
Right.
then we'd have big G very precisely.
Yeah. Yeah. Exactly. But the question is, which one is off and which direction?
Exactly. Yeah. But it's fascinating that we know the product so precisely, very accurately, for any given orbiting or any given central mass planet or whatever. I've always found that rather fascinating. So we can compute our orbital mechanics very precisely because of the product, big G times the mass always comes into play, and we know those numbers quite precisely.
Yeah. Hello, PhD Tony.
Oh, one other, pardon?
PhD Tony's out in the chat. Hello, Tony. I'm sorry, go
Well,
ahead.
something you might find rather interesting, seeing how you've been involved in discussions along with Dr. Bob and many others involving Coriolis. I had an interesting thing happen to me today. I was out at the shop getting my business set up in my new building, and a guy drives up in a truck and was submitting an application for work with me, and I was looking over his resume, and it was really quite impressive. This guy was, professional welder, mechanic. He's worked up in Alaska most of his life, worked on the pipeline there, flew helicopters, dropping pipeline in remote places and that, and had quite an interesting skill set. And we were talking about, building airboats and flying helicopters and various other things, and we started hitting on the topic of taking long-range shots with rifles. And it became obvious to me this guy really knew his stuff and knew what he's talking about. And it came out that he's a professional sniper, and he contracts out to many of our famous three-letter agencies. And and immediately a red flag went up. I say, is this guy pulling my leg? Is he bullshitting me or whatever? So I started asking him some questions to vet him out without trying to be too obvious, about what I was doing. And he answered every question correctly. And so, it was really registering that this guy could really be the real deal. And so I asked him, when he takes these long-range sniper shots, what does he have to take into account? I didn't mention anything in particular. I said, what kind of factors do you take into account when you do these long-range sniper shots? He says, you mean like the rotation of the Earth? And I said, yeah. It's called the Coriolis Effect. He says, yeah, I know. He says, we work those calculations out all the time. Says, among other things. And he was describing how he corrects for Coriolis and other factors that enter in that cause his bullet to drift off course. And I was asking him about some of the long-range sniper shots. He said, well, a mile is pretty common. He says, I've had a kill up at 1.75 miles. And I asked him, well, do you know what the long-range sniper shot is? And he knew exactly that it was a Canadian, an unnamed Canadian that did that. And he, this guy just seemed like the real deal. And he definitely knew what he about on long-range sniper shots. And he even told me things I hadn't even thought about in terms of correcting and things that they have to correct for because of the Earth's rotation and other atmospheric conditions. It was really quite interesting. We talked about long-range sniper shots probably for a little over 2 hours. It was really a fascinating conversation for him to tell me how he practices to compensate for Coriolis and other effects, and by you using tracer bullets. And also thing I hadn't thought about is you practice in mist in a misty day.
Yeah, so you
said
see
when
the
the
trail.
bullet goes out.
Yeah.
Pardon?
You can see the bullet trail.
Exactly. Yeah, just like a rocket going up into and hits, you know, through clouds or whatever, you see the swirls. And he was telling me how the effects about both gravitational force trying to pull a bullet down and Coriolis correcting that the bullet actually goes in a corkscrew.
Yeah.
And so it was really quite fascinating. But the takeaway on the thing is yes, snipers do correct for Coriolis.
Yeah, if you're taking a shot out to 1,000 yards, it probably doesn't make any difference. But when you move it on
I'm
out,
talking, you know, the guys that are doing the long range shots, you know, a mile or more.
yeah, when you go on out to a mile or a mile and a half, now the flight time becomes significant enough.
Right.
That,
Yeah. And of course, you know, he was pointing out how, you know, the direction of shot and where you are on the earth, this all comes into play and how they correct for it, you know.
Yep.
You know, you're going to get a different deflection whether you're shooting east, northeast, southwest, or whatever. And also if you're in the northern or southern hemisphere and all that. I mean, he knew it all. It was really quite fascinating listening to him because it's like talking to a physicist. I mean, this guy's been there, done that. He was a sniper in Vietnam and now contracts out. And he, like I say, he's the real deal. Not these bullshit artists that you hear coming onto these YouTube flat Earth discussions. In fact, I asked him if he wouldn't mind coming on to one of the shows and talking to the guys, and he respectfully declined.
good for him.
Yeah.
Good for him. Those morons don't deserve to hear somebody like that talk.
Yeah. Well, I didn't even tell him it was flat Earth or anything like that. I said I'm involved in some discussion groups where people are pretty interested in long-range shooting that, and I hadn't even mentioned that it had anything to do with nut jobs out there or anything like that. But he said no. He says nothing. You really can't have an effective discussion online, and he says I really have to be in the presence of people to really be able to describe this stuff effectively.
Yep, absolutely. So, hello, Facty, out in the chat. Have I proven gravity yet? You betcha. You betcha. I was pretty sure it was real to begin with, but now I'm totally convinced. And in a second, you're going to see some of the measurements that I've made so far pop up on the screen. Just a rough, dirty little spreadsheet. I'll wait till I see it here on the live stream.
So when you operate this apparatus and are proving gravity, what would be proven if your mother's sister operated it?
Same thing.
No, anti-gravity.
Oh, damn. George. It's too late for that. It's way too late at night for that. See if I get up to date. There's the spreadsheet. There's the spreadsheet. If you guys look at the over on the right hand side, let's see if I can. Well, I can just move things around if I'm not careful. Oh, I'm on Discord. I can't do that. Got a column of 8 black numbers and a red one down at the bottom. The red one is the average of 8 measurements so far. And the average that I've got right now, who knows how well this will hold up. And all this needs to be checked and rechecked. But At the moment, it looks like 6.65 times 10 to the minus the 11th. That's about 0.3% off from the known actual value. So I'm absolutely astounded at this point that it could have gotten that close. I think it's probably luck, and over time, as I make more measurements, that number's probably going to diverge a bit, but I don't know. We'll see. Maybe not. Maybe it really is that accurate. I don't know. But that's what we're looking at.
Well, I wouldn't dismiss it or discount that. I mean, after looking over your photographs and here the care and precision with which you built this thing, it wouldn't surprise me if indeed that is a real number. I mean, I'm really quite impressed with your woodworking. I mean, my gosh, if I were, I was thinking of building a Cavendish experiment myself, but after seeing what you've done, I just said that. Blue ribs, hands down. There's no way I could compete with what he's done.
Well, you got to have not a whole lot on your mind and a lot of time on your hands. This thing is.
Well, it's more than that. It's the woodworking skills too. I was looking at your joints, the wood joints, and other things that you've done here. I mean, it's really impressive.
Well, I just tried to imagine. And of course, I don't think the Cavendish actual experiment survived, not to my knowledge anyway. So I was trying to imagine what would have happened 220 years ago. But you know, that was from a day and age, a time when you had true craftsmen out there, not guys working in a factory. These were true cabinet furniture makers, and these are the sorts of wood joints that they would have used. That's what they would have known. That's what they would have known how to do. These are typical wood joints that have been in use since since the Egyptians. So I thought, well, that's my hobby anyway. That's what I do for fun, is make furniture and stuff. Hell, why not? I'll just design it that way and build it like it's a piece of furniture. And I'm glad I did that. Because you learn when you do that kind of woodworking, you learn to be very precise with things. And I doubt there's any part of that that's more than 5/1000ths of an inch off.
Yeah. So to make the grain stand out as you did you oil it or what?
It's got tung oil on it.
Okay.
Yeah, I use tung oil. Just to make it look pretty and make it.
Oh yeah, I mean it's beautiful.
And make it and protect it and so forth. So that if I don't want to put big greasy thumbprints or something on it. That's a pain in the ass to have to go back and fix. But I'm not sure that was the best idea. I doubt Cavendish finished his. And I may have exacerbated the static electricity problem by doing that. But whatever, we solved it. It's okay now. It just caused.
Well, I mean, what's going to be amusing and laughable is with these nut jobs you talk to on Jose's show. I mean, with any criticisms that they're going to have, of course, it's just going to be utterly ridiculous.
Oh, the big one is I'm not doing it in a vacuum, and that totally invalidates the test. And
right.
I hear that very frequently coming out of chemo.
Oh yeah, well, I mean, if you did have a vacuum chamber, then the complaint will be it's not a deep enough vacuum.
Right.
You're never going to satisfy the nutters, no matter what you do. So the
Yeah.
thing is, you just dismiss criticisms.
Yeah. The position I've taken with those guys is, if you are telling me that it's air current that's causing this, I'm telling you it's not. If that's your claim, then you need to build one of these things and prove it.
Well, the one thing you could do is just inside the cavity there where you have your balance beam, mount a few telltales that you can see through your window.
Yeah.
You know, some real sensitive telltales.
Yeah. Oh, I can tell you that there is no air current inside that thing.
Oh, I know there isn't. But I mean, if you wanted to give visual proof that there aren't, then, like I say, some real sensitive telltales, I've determined a way to build some really cheap, easy, very sensitive telltales if you're ever interested. But I mean, that. But then again, all you're doing is jumping through hoops for the idiots.
Yeah, and I'm trying to avoid doing that. I'm not going to dance I'm not their trained monkey. If they want to do this stuff,
Right.
they can do it themselves. If they want to prove it doesn't work, then build one and prove it doesn't work.
It's like I once made a cartoon for, remember Stingray?
Yeah.
Would come on, you know, the
Oh,
guy
yeah.
that's real good with optics and cameras, and that is, I sent him a cartoon once, and it was a bunch of flat earthers standing around, and he's kind of in the middle, obviously jumped up off the earth, and then looking down at the flat earthers and saying, "Is this high enough?"
Well, as you say, no matter what I do, they're gonna claim it doesn't work. It can't be. It's not right. And I really don't care. I didn't do this for them anyway. I'm not trying to prove gravity. Damn it, we already know gravity exists. Jesus, that's ridiculous.
Right.
Cavendish wasn't
Well,
trying to
you're
prove
right.
gravity either. Cavendish, all he wanted to know was what's the density of the Earth.
The Earth, right? Exactly.
Oh,
And from that, you could derive what Big G was. That followed afterwards.
yeah. He just wasn't interested at that point in time. Everybody was satisfied with the concept that Newton gave us, that the force is, the apparent force is proportional. Okay, well, there's clearly a constant of proportionality that turns proportional into equal. But it was another 100 and some odd years before C.V. Boyce got around to stating it in the form that we're used to seeing it in now. But
Yeah, I mean, Newton came up with the functional form of the relationship between masses and the force of attraction. He did not know what big G was, or in fact, it wasn't even coined then. It was just a constant of proportionality,
right,
which he didn't know what the value was, and that didn't matter. He was just looking for the functional form, and then developed the calculus to prove that he could assume that all the mass of a sphere could be considered to be a point source, all concentrated at the center. And
Yep.
that was an important aspect of that relationship, is being able to make that statement, and hence the development of the calculus to prove that. You know, and the same sort of thing came out with beforehand with Coulomb, and Coulomb developing his force law, which has the same functional form, but because they have the same functional form doesn't mean electrostatics and gravitational forces are in any way related. They just happen to have the same functional form, and that's because we're dealing with spheres, charge
yeah,
evenly distributed over the surface of a sphere, or a spherical mass. Hence, you're going to end up with an inverse square law having the same functional form just because of the fact that you're using spheres.
Yeah. Well, many things in nature obey an inverse square relationship.
Yeah.
You run into this all the
Just
time.
because the relationship. Yeah, just because the relationships are similar, proportional in the same way, directly proportional and inversely proportional with separation distance, doesn't mean that they're in any way fundamentally related. It's um, it's just that they are proportional in the same functional form. And then when you investigate it further and find what those constants of proportionality are, they're wildly different. Even though the functional forms are similar, the constants of proportionality are not similar in any way.
Yeah, the fact is, if we had elected to concoct some really, really, really awkward units of measure, you wouldn't even need a G.
That's true. Yeah.
Uh,
Well, we do that. Physicists do that down at the atomic level with um, electron volts and that sort of thing. Is in the Maxwell's equations, and that a lot of these constants disappear because of the units that are chosen, so that the constant of proportionality is unity.
Yeah.
And
yeah.
so that's done down at particle physics, I know, but I like myself dealing in the MKS system. I'm comfortable with.
Yeah, me too. It's easier.
Well, it's because that's what we've used, and I'm sure the physicists that deal with, electron volt units for energy and other types of units, it's just natural for them to be stating energy in electron volts rather than joules or microjoules or nanojoules,
Yeah, it's quite easy to work in those units. And it's really friggin' awkward when these morons want to talk about revolutions per minute, shit like that. Damn it. Could we stick with radians per second, please? Stuff like that just aggravates me. It just makes me do a bunch of math. A bunch of arithmetic I don't want to have to do.
Yeah. Or this stupid thing that they keep coming up with and trying to describe the spin of the Earth by tangential velocity at the equator. That's one thing that steams me.
Total crap.
I just want to scream every time I hear that.
Yep.
Trying to state spin rate in terms of miles per hour.
Nobody measures rotation in miles per hour. That's just crazy.
Well, it just goes to show the lack of understanding that they have in terms of what rotations are. They always seem to be fascinated by these large numbers. Well, we're moving at supersonic speeds on the surface of the Earth. Well, no. It's only relative to the center of the Earth.
Well, if you say it correctly, the Earth is rotating at 0.00007272 radians per second. That doesn't sound like much, right? Well, it sounds like what it really is. It, for all intent, it's barely moving. So that doesn't help them. They like that.
Expression is 72.92 microradians per second. It's easier to remember.
Yeah, 72.
It's very, very slow. It's a slow spin rate.
Yeah, absolutely. Very, very slow. And then you hear these absolute blithering idiots like Chris Berry, who cannot, for the life of to save his life, understand that the mass of the orbiting body is irrelevant. It doesn't make any damn difference if it's the size of the International Space Station or the size of a grape. If they're at that same, in that same orbit, they move at the same damn speed, for God's sakes. Mass just goes away.
Yeah, it is amazing in many kinematic relationships where you're dealing with motion of mass under a uniform gravitational field. Whole mass just drops out of the equations all the time.
Yeah.
And it just has, there's one fun comedy movie, I don't know if you've ever seen it, it's called Road Trip.
Oh, yeah.
It's where a bunch of college students from Ithaca, New York, took this trip to intercept a letter that one of the roommates had sent to his girlfriend down in Texas, and all the stupid shit they go get into, and they come up. I think this was in your area in Texas. They came across this river where the bridge was out, but the approach was still there, so they could take a run at it and launch their car to jump the river. And one of the guys in the road trip was a physics major, and they made a mistake in the thing. I caught it right away. He estimated how fast they were going to have to go, and made allowances for the weight of the car. Well, but
Yeah.
that's an interesting little problem in something like that, is you find that if you approach a ramp at a certain angle with a certain velocity, that's all you need to know. You don't need to know the mass of your car or snowmobile or motorcycle or whatever you're going to use to try to jump over a river, taking a run at a ramp. It's just the velocity and the angle of launch that's are important. It's mass independent.
That's right. Exactly. It simply comes down to acceleration being g times the big ball that we're standing on divided by the square of the distance between the center of it and any other mass you pick. No matter how little or how big. You're going to get 9.81 meters per second squared every time.
Yeah, well, this is what happens in in Jose's shows. These arguments go on endlessly over the same thing day after day because you're dealing with math and physics illiterate, very undereducated people, and so they're never going to get it. All the time they spent on Jose's show, they could have taken a college course at a local community college and understood some of this stuff, educated themselves, but no, they rather just sit and spin their wheels, stay in the muck, spinning their wheels, arguing the same thing day after day and going nowhere.
Hell, you don't even, if you wanted to, if you truly had any interest in it, you don't need to even do that. You can do it for free on the internet. You can go on YouTube and get an MIT education if you want to.
Well, that's true, but most people don't have that sort of drive and self-discipline. There really is no substitute for most people to be in a classroom setting where you have guidance and motivation and a strict schedule to follow.
Yeah, I agree.
Left to our own devices, we tend to not follow a schedule, whereas if you pay for something and required to be there every day at a certain time, that helps you in the learning process. It takes a rather unusual individual to have enough self-discipline to get through just one course on your own with self-study.
Yeah, it won't work for everybody, but if you've got that, I mean, if you really wanted to, you could do it. You
Oh
can
yeah,
do it.
yeah, very definitely.
And the cool thing is, you don't have to go home and wonder what if you actually heard the professor correctly. Just rewind the damn tape. Set back 5 minutes and listen to it again. And there are some excellent, excellent lectures out there by, what's his name, Walter Lewin.
Oh yeah, yeah. He's one of my favorites. He's done many excellent videos.
Oh, he has. He has. He's one of the few people I've run across in my life that can actually explain a damn gyroscope and make people understand it.
Yeah.
Probably the least obvious device on this planet is the damn gyroscope. Anybody that looks at one and doesn't know how they work to begin with and says, oh yeah, that's what I expected it would do, is lying to you.
Right.
Nobody can look at it and say, yeah, that's what I expected. Bullshit.
Yeah, it's very counterintuitive.
Yep, totally. Totally. Your friend Rocky has been frequently misquoting you lately.
Oh gosh, yeah, I gave up on him. He's been nothing but a liar and a slanderer. I have no use for him. What has he done now?
Well, he's back to the same rhetoric that he's always coming up with, talking about how he has measured 2.3 miles of horizontal line over still water, showing no drop at all.
Yeah. Well, that's in
But you know the
full-face
story.
lie, because once alone with him, I pinned him down on that, and turns out he's never ever done any of that. The most he's ever measured is in steps of maybe several hundred feet. He's never
Right.
done one long shot like that.
No, and I've pinned him down too. Same thing. And he absolutely refuses. He understands our model as well as we do. He's just lying about it. But he talks about
Yeah, I can't imagine him not. I can't imagine him not understanding the fact that if you take an auto level and move it forward several steps, that you're just going to be following the curve of the Earth. You're not going to be establishing a straight horizontal line. I mean, I've explained it to him many times. Rumpus has done, and unless he's a real bona fide imbecile, there's no way he can't understand that. But he could be a complete imbecile.
I think he is.
I won't discount that possibility.
Well, I asked him, might have been today, I don't remember now, if he had any idea why manufacturers make things called auto levels and then tell you you probably shouldn't use them past 300 or 400 feet. Do you have any idea why they might tell you that it's not a good idea to go try to shoot a level that far out? Oh, I got an idea. Because it won't be friggin' level if you go out there a mile.
Wait. Okay. Yeah.
If you
You're
use,
shooting tangent,
yeah,
which isn't following the curvature of the
it's
Earth.
not following the curve, exactly. They don't want you doing that. They want you to step your way around the curve
Yeah.
if you expect to
Yeah,
be level.
normally, yeah, if you look in any surveying manual having to do with auto levels or manufacturing um, manual for your auto level, is to say, they'll say, is um, use it within, like you say, 1 or 200 feet. Anything beyond that, you have to take into account the curvature of the Earth and make appropriate corrections. But if you don't want to make corrections, then you have to limit yourself to about, a couple 100 feet at most.
Yeah, and at a couple
Anything further than that, then the curvature drop tends to be outside the or greater than the amount of resolution of the auto level. The auto level will start picking it up at that point.
Yep. Yeah, exactly. A few 100 feet out, you're only a few thousandths of an inch. But at a mile, you're 8 inches. And it wouldn't be good to pour concrete that's 8 inches high a mile. Yeah, somebody's going to be pissed.
What I've kept telling them to do, and I know he hasn't done it, neither has Bev or any of these others, is a very simple test. All you have to do with your auto level is it'd even be better with 2 auto levels, but you could do it with a single auto level. You set it up first, get it all leveled up, and shoot a range pole a mile away, and get a mark on that range pole to where level is from your observation point, and then move your auto level to that pole, or first set your auto level up and set a range pole, 2 range poles, one at near the observation point and one, say, a mile away. And then you shoot both range poles and you put a mark on both poles of where level is. Then you move your auto level to the far range pole and shoot back to the original position. You first position your auto level so that its optics are at the center of the mark at the far range pole, and you shoot back to the first one to see if you can see the mark, and you'll find that you'll be shooting high by
about 16
twice
inches.
the drop.
Yeah.
Yeah.
Yeah, by about 16 inches.
Now,
Because you'll double your area
and if
doing
the
that.
Earth was truly, and if the Earth was truly flat, you'd be hitting the same mark.
Right, but you will not. Yeah, the air is doubling when you do that.
Yeah, and that's a very simple test for anybody to do. I mean, you could rent an auto level probably for less than $50 a day.
Oh,
Go
yeah.
out and try it yourself.
Well, Rocky claims to have all this stuff anyway.
Yeah, well, he has, people that use the equipment working for him. I doubt that he uses much of the equipment himself. Probably the first time he ever used an auto level was maybe months ago when he got involved on Jose's show and people started challenging him. I doubt that he's probably even really used any of the equipment prior to that.
Well, pouring concrete, he probably has used an auto level. Some. But I'll bet.
Yeah, for maybe slabs and stuff, but
But
nothing where he's really had to understand
Right.
the true operation of an auto level and how a curved earth affects it.
I built a bunch of houses years ago. And I got quite accustomed to the way those guys do things. And most of the time, they're not going to pull out an auto level. They'll pull out a laser, one of those spinning lasers,
Right.
and set that up because it's easy. You got the little sensor thing that beeps, and lets you know whether you're high or low or on it. But on it could be, plus or minus half an inch, which is perfectly fine if you're pouring a footer, and good enough for setting pins for pretty much pretty much anything. I'll bet you most of what he does is that. And a lot of the time, I know what he does. I mean, I've seen pictures of his crew. He's shown some stuff from time to time. Nobody does a damn thing when you're pouring a driveway or a sidewalk. Jesus Christ.
Right. You can kind of eyeball that.
Yeah, get the bobcat out there, scratch around, get it, make it look kind of level. Pour the concrete and be done with it.
Yeah, most of the time on something like that, you'll just maybe set up some 1x6s or on the edges, and then screed your concrete with a long 2x4 between the two and just run it along the rails.
Yeah. 1x4s usually.
Yeah.
Because that's the common thickness for normal residential stuff.
Right.
Which is one of the trick questions on a general contractor's exam. I'm dying to ask that to Rocky one of these days. What is the minimum thickness of concrete poured over gravel? And I'll bet you a nickel he'll say 4 inches. And he'll be wrong. According to the International Building Code, it's 3.5 inches. And there's a reason for that, because we use 1x3s for forms.
Yeah.
I mean 1x4s for forms, and a 1x4 is 3.5 inches wide.
Yeah, out here we typically do about 6 inches because of frost heaving in the spring.
Oh yeah, you guys have got other issues. You're going to be setting foundations down 3 or 4 feet.
Yeah, you have to use a grid of rebar, a grid maybe with 1 foot squares to lay out a pad. Otherwise, you're asking for the stuff to crack.
Yeah, oh yeah. What's your frost line up there, George? 4 feet or so? Something like that?
Oh, 5 to 6.
Okay, yeah. Yeah, I live here in Tennessee. Our frost line is about 8 inches.
Yeah. Well, it can get pretty ugly in the spring when the frost starts coming out of the ground. I mean, cripe, you'll find mounds in the middle of driveways or say back roads where you don't have a real good base, and you've just laid down an asphalt pad. You'll have the doggone thing boils coming up 8-10 inches high up off the pavement,
Oh hell yeah,
breaking through.
that stuff's gonna heave.
Yeah.
We don't have that
Well,
issue.
one of the things they found that works really quite effectively is this plastic fabric looks like the weed stop fabric in the sense that you put in gardens and stuff, except this stuff is a much heavier, robust weave. And by laying that down, you prevent a lot of these frost issues.
Yeah.
And settling and movement of the foundation. It really works quite effectively.
Give me about 30 seconds, George.
Yeah, like sewer and water lines, typically they're laid down anywhere from 12 or 10 to 12 feet under the surface. That's why we don't have the water problems that Texas and you guys have after that winter storm.
Yeah, sorry, I stepped away for a minute. So, where is this thing settling down at? I wonder. Top number looks like 213 maybe. And on the bottom end, it's around 206. Just curious. We'll just take the average of those. So 209. And we started at let's see, I can go over here where I can see it easier. 238. 238 and a half minus 209 and a half. .29 millimeters. Yeah, that would give us a value of G of about 7.1, something like that. But I'm not sure about those numbers because I'm looking at this little tiny YouTube screen is all I can see of the replay. I have to go back and look at that. On the actual stream and see where we're at. That's what happens though. You get one is high and one is low, and that's the reason why we make lots of measurements. Well, George, I'm going to give it up for the evening.
Yep. Yeah. Sounds like a good idea. Time to maybe get a little shut-eye. I haven't been doing very well myself either lately. In the last 4 days, I've pulled 3 all-nighters.
Wow. Well, thanks to everybody out in the chat that's didn't have anything better to do tonight. Appreciate you guys showing up. It's been fun. And we'll do it again pretty soon. I'll get some of this data cleaned up and reduced, checked and so forth, and we'll see where we're at. Just gotta continue to the end. Make sure we get this right. So with that, I'm going to end the stream at this point. You guys come back.
What I'm going to do, I'll give you some competition come spring, is so people have an alternative to watch the slow oscillation. I'll set up a webcam in my yard, and people can watch the grass grow as an alternative.
Might be easier to see the grass grow than it is to see this damn laser move.
All right,
Terrific.
well, I'll catch you later.
All right. And I'll see all you guys later. Good night.
All right. Okay, later, Blue. Take care.
Yeah, see you, man.